Hello there, welcome to this lesson. This is a continuation of the exam preparation series, and the topic in this lesson is sequences and series. So let's take a look at the question. Alright, so we are asked to determine the maximum number of pentagons that can be formed if there are 100 candles available. So with investigation that I have here on the board, we can clearly see that there are 5 candles used for the first pentagon, for the first diagram, and there are 9 candles, the second one, and the third one has 13 candles. So clearly this is an arithmetic sequence. What do we need? We need this guy right here. That is the general formula for arithmetic sequences. Ensure that you copy and paste it correctly because you are given a formula sheet and therefore you have no reason to get it wrong. Okay, so what do we need? We need to know what is our first term. Do we know it? Yes, it's 5. We need to know what is our constant difference. Do we know it? Yes, it's 4, right? And that 100 that is part of the information given in the question will come in here because we want a maximum number of pentagons that can be formed if we have 100 candles available. So it's a relationship between the number of pentagons and the candles that are available. Okay, so we have 100 equal to 5 plus n minus 1 times 4. Let us work neatly. We can just transpose the 5 and have a 95 here. Then we have 4n minus 4, transpose the minus 4, becomes 99 equal to a 4n. How do we solve for the maximum number of pentagons? We have 24 and 3/4 that will result here. So this is a proper fraction, but doesn't represent a whole. Okay, remember a pentagon is a complete shape. So the maximum number of candles that can be formed with 100 candles available is definitely 24. Therefore, 24 pentagons can be formed with 100 candles available. Okay, so this takes care of question 4a. Let us move on to the next question. Take a look. Alright, so we now have an arithmetic series and we can expect to work with the sum formula because we are given the sum value of some n terms being 300 in this case. So the 3 quantities that are given here, the first term is 3. What does the first term represent as well? The value of a, and Tn, we're told that the last term is 47. What does this represent? That is the value of L. If you use the sum formula that involves the last term, you'll recall that then you will need to use that 47 in place of L. Okay, the very first question is determine the number of terms that exist in this situation, right? Where if you add up all the terms, you get 300. So what do we need? Sn equal to n over 2a plus l. Okay, we have Sn, we don't have n, we are looking for n. A we have, L we have. So by substitution, we have 300 equal to n over 2, 3 plus 47. What do we get there? 50 divided by 2 gives us what? 25. And then we still have the n there. How do we solve for the number of terms? Division both sides by 25, and therefore n is equal to 12. Okay, so there are 12 terms in this series such that when you add all these 12 terms, you get 300. Okay, the first term being 3. Great stuff. The next question is to determine the common difference, or the first constant difference. We understand that this is an arithmetic sequence, so we need to pick the right equation that will help us. And which one is that? It's this one. A plus n minus 1 times D. Okay, so what do we need? We need Tn. Do we have Tn? Yes. Do we have A? Yes. Do we have N? Yes. We just need D. So let us substitute correctly. 47 is equal to what? 3 plus 12 minus 1 times D transpose the 3, you have a 44 there, equal to 11D. And therefore the constant difference is a 4. Okay, so this is B1 and this will be B2. Just keeping to the numbering that is used in the question paper. Okay, so this takes care of question B under question 4. Clearly straightforward questions, and we should be getting full marks then. All right, let us jump on to question C, still under question 4. Take a look. All right, so now we have a question that involves sigma notation, and of course we understand by now that this involves summing a number of terms to get a particular value, and that's why typically you'd be asked to calculate this or evaluate this. So what is this that we need to calculate or evaluate? We need to understand that this symbol means sum. So what is this? Your lower limit is 2, your upper limit is infinity. So sum of infinite terms. So this reminds of what type of series? Geometry, right? So we're summing infinite terms in a geometric series. Even the rule definitely confirms that for us, that we are dealing with a geometric series. Okay, is it in standard format? No, we have a power of n plus 2. So what will be the roadmap here to the solution? We will need to perform expansion, and this symbol here must always remind you of that process, expansion, even though it means summation. That is one way of getting at least the first 3 terms to get your constant ratio in this case, so that you can use it properly in the equation as well as the first term. Okay, so what will be term 1? This is your lower limit. It is telling you to start at 2 all the way to infinity. So if you're looking at the number line, we are moving from here all the way to infinity. Don't go to 1 or 0 or anything like that. Okay, so we substitute 2 in place of n to get the value of term 1. Okay, so let us get that right. 4 times 1 over 2 to the power of 2 plus 2. What does this give us? 1 over 16, right? So this becomes 1 over 4. Okay, T2, after 2, what is the next natural number? It's 3, right? So 4, 1 over 2 to the power 3 plus 2. Okay, what will the power give us? 1 over 32 times 4 gives you 1 over 8. The last one, let's do the last one. The next natural number here will be 4. Okay, so it's 4 times 1 over 2 to the power 4 plus 2, giving you what? 64, right? I mean 1 over 64 times 4, giving you 1 over 16. Okay, so to write it clearly for you, we have this type of geometric series, and we can actually write it properly to say we are summing infinite terms. Okay, summing infinite terms. So the a value here is 1 over 4. The r value is 1 over 8 divided by 1 over 4, giving you 1 over 2. Is it convergent? Yes, because r is between -1 and 1. Okay, are we ready to get the value of this summation? Yes, sum to infinity is equal to a over 1 minus r. We have 1 over 4 over 1 minus a half, giving us 1 over 2. Okay, so definitely summing all these numbers to infinity, it will converge to 0.5 or 1 over 2, because all of them are proper fractions, and indeed it does make sense that it will be the correct answer there. This takes care of question 4c. Let us go to the last question under question 4, that is question D, and yeah, here it is. Okay, so we now have a geometric sequence that is given, and there is some unknown term that involves p as the variable, and the other two are known. T5 is 4, T7 is 1, but T3 is given as an algebraic expression, and we're asked to determine the value of p, knowing that this is a geometric sequence. So what then do we think about? Yes, a constant ratio. Okay, so we are given odd number terms. What you need to understand about the constant ratio is that yes, we find it between consecutive terms, T1 and T2, T2 and T3, T3 and T4, like that. But there is also a constant ratio that exists between even terms, yes, 2, 4, 6, like that, and also it exists between odd terms, T1, T3, T5, T7. Definitely numerically won't be the same, but there is that maintenance of that property of a geometric sequence within the main one. Okay, so what do we need to do? We know that T5 over T3 is equal to T7 over T5. So you still need to maintain the order of taking the ratio between consecutive terms or consecutive odd terms in this case. All right, so what do we need to do? Substitute now. 4 over 5p plus 1 equal to 1 over what is T5? 4. Cross multiply, we have 16 equal to 5p plus 1. Transpose the 1, you have 15 equal to 5p, and therefore p is a beautiful 3. Okay, so this takes care of this question, and this is the end of question 4. So thank you for tuning in. Ensure that you be on the lookout for question 5 and 6 video as we continue moving along into section B of the paper and eventually completing the paper, of course. So thank you for tuning in. See you next time. Sharp, sharp.